Okay, I think we are recording now.
Okay. So this is our homework one report submitted by Team 1. Template page. These are all the members. We have our revision history on just a description of like who made what changes to the document and our table of content according to the homework outline. So we have all of the everything that was in the homework outline except exercise 3 because this is still part of the homework 1. And all right, so now jumping in on the big picture, like where we're at. Like so we have the core concept of F-dome, which basically your Cal State Fullerton's own localized air defense shield against drones, missiles, or like any airstrikes or airborne objects that could like harm their university. So we're the point of this homework assignment is to build architecturally significant requirements that are going to shape what our product is going to look like. And so this we have functional requirements, non-functional requirements here, our system context diagram, which should show you a bird's eye view of like how this air defense system interacts with any external entities. For like external like defense systems, your defense operator, satellites, maintenance engineer, and just all these details. So that's what our system context diagram will show you. Now, the technical environment here, so this just shows like what we're dealing with, right? We're dealing with a cyber physical environment, data from radars and satellites will hit the system at different rates. So like we need to make sure that we have industry standards and best practices being followed, right? So for example, like latency is a key. Like if fast moving threat enters the airspace, the pipeline to detect, classify, decide, and respond needs to be complete in under 2 seconds. So that's just one of the non-functional requirements that we're building our technical system around, and the tech stack considerations and like the NATO standards applying. And when it comes to the domain knowledge, like this is your air defense pipeline, right? The classic how like a broader version of your air defense system, like the classic workflow applies here, like surveillance, tracking, threat evaluation, weapon assignment, and engagement assessment. So yeah, just because of these risks, our architecture relies on a layered decision support model. We separate the automated math from the high risk actions, and that's what we try to figure out in the domain knowledge. Okay, now I'm gonna pass it on to Wendy to cover system features.
Okay. So essentially, the FDOM system is designed to protect the CSUF campus from any airborne threats. It uses satellites, radars, detectors, and trackers to detect when any airborne object enters the monitored area. And once an object is detected, the system's going to classify it as friendly, unknown, suspicious, or hostile. It's also going to track its location, speed, and the predicted path. Um, and based on this information, the system's going to evaluate the severity of the threat and alert any defense operators if needed. It will also recommend any countermeasures, like if it needs to use like a missile or a gun, laser, or electronic jammer. Um, but before any defensive action can be taken, though, the system's going to verify that the defense operator has the appropriate authorization. And the system's also going to monitor the health of its um, devices. And yeah, it's going to record all detections, alerts, operator actions. And then if you scroll a little bit down, you can see the use cases and then the use case diagram below showcasing the use case diagram. Yeah, and then moving on to the next person.
Okay. Mm, The next part is the system quality attribute and the scenarios. We have 7 quality attribute, and we need to define each attribute to better fit to our defense system. And we also need to evaluate how they impact both business value and architectural design. Like for the availability, we want that if the read node fails, the system show continuous read tracking using alternative sensor without interrupt operator visibility. And like for the testability, we hope the engineer should be able to simulate attack and verify system response without connecting real defense hardware. So we came up with each concrete scenario requirement for each QA. And for the availability scenarios, we break down each specific scenario into its core elements. Like for the availability scenario, the stimulus is from the reader server, and we hope the system will respond with switch to backup data source and continue tracking. And we measure it with, we hope it recover within 5 seconds and continue showing threat information. For interoperability scenario, when there is a external defense systems and the threat information, the system should receive the information, convert it into a format it can understand, and update the threat analysis without interrupting normal operation. For modificability scenario, the hardware team add a new laser defense device development, connect the new device to a system without changing the existing threat detection, tracking, or decision-making functions. For the performance scenario, we hope the threat intermonitor airspace is from the incoming missile, and the system will response analysis the threat and generate the response recommendation. It need to be completed within 2 seconds. For secure scenario, if there is an unauthorized access attempt from hacker, and we hope the system will block it with a 100%. For testability scenario, for the new function development completed, the following task we was executed, and we will run a replay test, capture activity, publish text report. And for the usability scenario, it will work on normal operational with a thread and the response with a clear status. It will be saved valid action within 10 seconds. So that's all for this part.
Elena, you are muted.
Oh, sorry. Okay. Oh, okay. Okay, for our system, we define monitorability as the ability of the system to expose what is happening inside while it's running. This is different from regular logging. Logging records what happened after the fact, and the monitoring ability is about dictating a program early in life that someone can actually respond to it. So now we talk about the general six parts. The source of stimulus can be a sensor, a service, or device, or an operator, and the stimulus is something going wrong, like the data not updating or a device lost the connection. And the artifacts and the environment covers all the system models, like the normal or an emergency. And the response is that the system detects the programs and update the status, display, send an alert or save a log. And the response menus is that the alert must include the components or last update time, current impact, and recommend action. Now we talk about the our concrete scenario. Just imagine the system is tracking an unknown flying target during an emergency. At this moment, the long range radar data screen has not been updated for like the 15 seconds, and if the system keeps display the tracking information without an warning, the operator might believe that the data is still right, but it's not. So monitoring service should detect this data, mark the radar as degraded, reduce the confidence level of the tracks, and clearly notify the operator about what happened. This is why we treat the monitorability as a first-class cognitive attribute for our system. A visible fault, a fault cause inconvenience, but an undetectable fault is more dangerous because it might cause operator to believe the system is working normally, while in fact it has already lost its reliability. Okay.
Okay, I'll do the next part. Okay, so for our exercise 2, we conduct the quality attribute workshop process and assigned every team member with different stakeholder roles. And so each of these roles, they should come up with the most important business goals they think as their roles. So here is a table for our recording of this process. As you can see, each of us is assigned with a specific role, and each of us come up with the business goals we think is the most important. And in this design quality attributes, we marked the red dark color with uh, the quality attributes we think is the most important, uh, which is availability, performance, and interoperability. And they are always high business values and high architecture impact. So these three quality attributes are our architectural drivers. And the next is our utility tree.
Okay, for the utility tree, our goal was to organize the important quality attributes instead of treating all of them as equal. After the QW discussion, we focused more on availability, performance, and interoperability because they had both high business value, and high architectural impact. For example, if a radar server fails during an emergency, FDUMI should keep checking threats through backup sensors and recover within 5 seconds. For performance, the system needs to analyze a misleading threat and recommend a response within 2 seconds. Then, in the ADRT, we connected these requirements to actual design choices. For availability, we used the tactics such as active redundancy, reconfiguration, and heartbeat monitoring. For performance, we consider the event prioritization and concurrency. For interoperability, adapters and service-oriented architecture helped us handle different external systems and formats. The main lesson we learned is that architecture is not just picking patterns. We have to explain why a tactic fits a scenario, and we also have to consider trade-offs. For example, stronger security may add complexity or slow down response time. Finally, the rest of the report includes our reference, team chatter, is this, and team evaluation. That's all. Thank you.